Hello, I'm Mike McCulloch. Today I'd like to talk to you about something which is still quite controversial, but also very interesting, the Allais effect. And I'm talking about this because in the UK we're waiting eagerly for a partial solar eclipse, which is due to happen in about an hour or so, or to start in an hour or so. So I thought it'd be an ideal opportunity to talk about this, because what Maurice Allais did back in the 50s, in 1954 and 1959, was he was monitoring what's called a paraconical pendulum, which he had in Paris, and he happened to be monitoring it during a partial solar eclipse in 1954. Now, this pendulum was about 83 centimeters long, and its swing was about 5.7 degrees, and he was monitoring it very carefully in a closed environment and restarting it every 20 minutes, measuring the amount by which the pendulum rotated. Now, this is interesting because these pendulums, Foucault pendulums they're called, they tend to remain, they like to remain stationary in absolute space as the Earth rotates beneath them. So when you look at them, it appears that they're actually moving, that their plane of oscillation is actually moving clockwise relative to the Earth, but it's actually the Earth that's rotating anti-clockwise underneath them, and the pendulum is staying more or less still. So in monitoring this pendulum, Allais found that during a partial eclipse, the pendulum suddenly sped up in its clockwise rotation, and it kind of rotated by about 10 degrees over time. And then at the end of the eclipse, or in the second half of the eclipse, it went back by about 10 degrees, back to where it had been. And various reasons for this have been suggested, but none of them by itself can explain this effect. The atmospheric density changes, for example, that have been proposed, but none of them, as far as I can see, can explain it. Now, in talking about this anomaly, I'm not saying it's necessarily true and that it's necessarily unexplained. There might be an explanation that I just don't know about, or that people don't know about. But I think in science, it's important to keep the idea that you have to keep pushing. You have to keep trying these, looking for these observations, which are usually controversial because they interfere with fundamental physics. They seem to challenge fundamental physics. So it's quite problematic mentioning them. People don't like it. But this is exactly the sort of anomaly that we want to challenge mainstream physics, because we want to advance, we want to improve it. So that's why I'm talking about this. Not that I'm 100% sure it's correct, but because I'm 100% sure it's valuable to do so. So this anomaly is, as far as I know, unexplained. But a few years ago, I worked out a way that quantized inertia might explain it. And so I'm going to try and explain that. So in quantized inertia, the inertial mass varies in a new way. So this is a formula for it. So the m prime is a modified inertial mass. The m on the right-hand side is the original normal inertial mass. And then the factor there is 1 minus 2c squared over a theta, where c is the speed of light, a is the acceleration of the object, and theta is the cosmic diameter, a very big number. So this equation shows that when accelerations get very small, so the a on the right-hand side, then that means that second term blows up, and it reduces the factor, and it reduces the inertial mass. So that's how it works, and it works very well for galaxies. At a galaxy's edge, the accelerations are very small, so a becomes small, so that term also becomes small and the inertial mass goes down. So that means that for stars at a galaxy's edge, quantized inertia predicts they have less inertial mass, less centrifugal force, and so you don't need dark matter to hold a galaxy in. Now, the interesting thing I noticed about the Allais pendulum was that if you regard the plane of oscillation of the pendulum as being a thing, then its acceleration as it goes around in space, sort of as it twists in space, that acceleration is of the same order of magnitude as the acceleration at the edge of galaxies. And so you might expect that this plane of the pendulum might be subject to quantized inertial effects. So what happens in a solar eclipse is that the moon obscures the sun. So before that happens, there are a lot of mutual accelerations between the pendulum and the hot sun, the atoms in the hot sun. And I've talked about this in another video. It doesn't mean that we should consider those accelerations in a galaxy rotation, the heat of each star in a galaxy rotation, because it's symmetrical about the star. But we can consider it. We can consider the heat in the star from the point of view of a pendulum, or its plane. So what happens when the moon covers the sun is that suddenly these mutual accelerations are blocked by the moon. Perhaps this is what I'm suggesting, and I'm only suggesting it because I made it to work mathematically. So it seems to work. So it's interesting. I'm not saying it's necessarily correct. I'm just saying it's interesting. So it turns out that you can work out, and it takes a few pages to do it, but I managed to work it out, that when the plane of the pendulum's oscillation loses its contact with the sun, suddenly it has an incredibly small acceleration. It's only got this very small acceleration, so it loses inertial mass. And in order to conserve angular momentum between it and the spinning Earth below it, it has to move clockwise. So how much clockwise? Well, I worked it out, and you can come up with an angle, which is shown here. Theta is 8 times 10 to the minus 5 times the half period of the eclipse, this t to the 0.5, t 0.5, divided by the length of the pendulum, which is about 0.83 meters in this case, divided by sine of the latitude that you're at. And if we put, so the observed shift in the plane of the pendulum was about 10 degrees, and when I put numbers into the to this formula, I got, for the eclipse in 54, I got 6.4, and for the other one in 59, I got 7.4 degrees, which is not very far from 10 degrees, and certainly agrees given the uncertainties in all these parameters that I've used, like the cosmic diameter, for example, has a 10% uncertainty. So it does seem to work, and it does make some predictions as well, because if we look at this formula, if you see that you should be able to vary the shift in the pendulum's plane should vary as with the length of the pendulum. So as the pendulum gets longer, the shift should decrease. And if you go to lower latitudes, also this sine theta will decrease. So that will mean that theta, the angle of deviation, should increase at low latitude. So yeah, so that's the Allais effect, and quantized inertia may be able to predict it. Okay, so that's it for today. I'm looking forward to seeing the partial eclipse here very, very soon, and I look forward to making another one of these for you tomorrow. Goodbye.